Welcome. Today we will see problems on pressure vessel openings. Openings means nozzle openings. Now this is the first problem. A pressure vessel consists of a cylindrical shell with an inner diameter of 1500 mm and thickness of 20 mm. It is provided with a nozzle with an inner diameter of 250 mm and thickness of 15 mm. The yield strength of the material for the shell and nozzle is 200 Newton per mm square and the design pressure is 2.5 megapascal. The extension of the nozzle inside the vessel is 15 mm. The corrosion allowance is 2 mm while the weld joint efficiency is 0.85. Neglecting the areas of welds determine whether or not a reinforcing pad is required for the opening. If so, determine the dimensions of pad made from a plate of 15 mm thickness. Now we will see its solution. Now this is the given data. For cylindrical shell, DI internal diameter DI is equal to 1500 mm. Thickness small t is equal to 20 mm. For nozzle, small di, that is nozzle diameter, inner diameter di is equal to 250 mm. Tn, that is thickness of nozzle, is equal to 15 mm. H2 is equal to 15 mm and internal pressure Pi is equal to 2.5 megapascal. SYT, that is yield strength, is equal to 200 Newton per mm square. Corrosion allowance Ca is equal to 2 mm and efficiency is equal to 0.85. And for pad, thickness small t is equal to 15 mm. Now this is the diagram of nozzle, in which it is seen that there are various areas, thickness, diameters, height, then different dimensions such as x, t, tr, trn. Different areas are there: a1, a2, a3, a4, a. Therefore we will see their notations or what is the meaning of that different notations. Let capital A is equal to area of metal removed in corroded condition mm square. D is equal to inner diameter of opening in corroded condition. Therefore small d is equal to di plus 2Ca in mm. Small di is equal to inner diameter or nominal diameter of nozzle wall in mm. Tr is equal to required thickness of cylindrical shell in mm. Small t is equal to total thickness of the wall of cylindrical shell in mm. Tn is equal to total thickness of nozzle wall in mm. Trn is equal to the thickness required for the nozzle wall to be able to withstand the pressure in mm. Small w is equal to width of the pad in mm. A4 is equal to area of reinforcing pad in mm square. A1 is equal to area of axis thickness in the vessel wall in mm square. A2 is equal to area of axis thickness in the nozzle wall in mm square. A3 is equal to area of the inside extension of the nozzle in mm square. Therefore, step 1 of this problem, in that we will find out area of the removed metal. For that we will find out first of all sigma t, that is allowable tensile stress. Sigma t is equal to SYT upon Fs. Fs means factor of safety. Therefore, factor of safety is 2.5. Therefore, sigma t is equal to 200 divided by 2.5. Therefore, we are getting sigma t is equal to 133.33 Newton per mm square. Now we will calculate Tr, that is required thickness of cylindrical shell. Therefore its formula is TR is equal to PI DI divided by 2 sigma T into efficiency minus PI. Substituting the values, therefore TR is equal to 2.5 into 1500 divided by 2 into 133.33 into 0.85 minus 2.5. Therefore TR is equal to, we are getting it as 16.73 mm. Then let small d is equal to inner diameter of opening in corroded condition. Therefore small d is equal to di plus 2ca. Therefore substituting the values, which is equal to 250 plus 2 into 20, that is 2 into 2, which is therefore d is equal to 254 mm. Capital A is equal to area of metal removed in corroded condition. It is given by A is equal to d into TR, which is equal to 254 into 16.73. Therefore capital A, we are getting it as 4249.42 mm square. This is equation A. Step 2, area available for reinforcement. Let TRN is equal to thickness required for the nozzle wall to withstand pressure. Therefore TRN, its formula TRN is equal to PI DI divided by 2 sigma T neta minus PI. Substituting the values, 2.5 into 250 divided by 2 into 133.33 into 0.85 minus 2.5. Therefore TRN, we are getting it as 2.79 mm. That is thickness required for the nozzle wall. The limiting dimension x is the higher of the following two values. Therefore x, first value x is equal to small d is equal to 254 mm, or x is equal to into bracket di divided by 2 plus tn minus 3 ca. Substituting the values, x is equal to 125 plus 20 plus 15 minus 6. Therefore x is equal to 154 mm. Therefore comparing these two values, we will write x is equal to 254 mm. The limiting dimension h1 is the lower of the following two values. Therefore h1 is equal to 2.5 into bracket t minus ca. Substituting the values, 2.5 into bracket 20 minus 2. Therefore h1 is equal to 45 mm, or h1 is equal to 2.5 into bracket tn minus ca. Substituting the values, therefore h1 is equal to 2.5 into bracket 15 minus 2. Therefore h1 is equal to 32.5 mm. Therefore we will compare these two values and we will take its minimum value. Therefore h1 is equal to 32.5 mm and h2 is equal to 15 mm. The areas available for reinforcement within the above limits are as follows. A1 is equal to 2x minus d into bracket t minus tr minus ca. Therefore substituting the values, 2 into 254 minus 254 into bracket 20 minus 16.73 minus 2. Therefore A1 is equal to 322.58 mm square. A2 is equal to 2h1 into bracket tn minus trn minus ca. Therefore A2 is equal to 2 into 32.5 into bracket 15 minus 2.79 minus 2. Therefore A2 is equal to 63.65 mm square. A3 is equal to 2h2 into bracket tn minus 2ca. Therefore substituting the values, 2 into 15 into bracket 15 minus 4. Therefore A3 is equal to 330 mm square. Therefore adding these three areas, A1 plus A2 plus A3, we are getting it as 1316.23 mm square. Equation B. Therefore step 3, if area of pad from A and B, we will write again these two equations. Capital A is equal to 4249.42 mm square, and A1 plus A2 plus A3 is equal to 1316.23 mm square. Equation B. Therefore it is clear that capital A is greater than, that is area A is greater than addition of the areas A1 plus A2 plus A3. Therefore a reinforcing pad is necessary. The area of the reinforcing pad F4 is given by A4 is equal to A minus into bracket A1 plus A2 plus A3. Substituting the values, we are getting 4249.42 minus 1316.23. Therefore A4 is equal to 2933.19 mm square. Now step 4, dimensions of pad. The thickness of the reinforcing pad is 15 mm. Therefore the width of the pad W is given by W is equal to 2933.19 divided by 15. Therefore W is equal to 195.55 or 200 mm. The inner diameter of the pad is equal to the outer diameter of the nozzle, that is 250 plus 30, which is equal to 280 mm. Outer diameter of the pad is equal to 280 plus 200, which is equal to 480 mm. Therefore this is the end of the first problem. Now we will go to second problem. The cylindrical shell is subjected to an operating pressure of 0.75 megapascal. The yield strength of the plate material is 200 Newton per mm square and the corrosion allowance is 3 mm. Spot radiographed double welded butt joints are used to fabricate the shell, whose internal diameter is 2.5 meter. Torus spherical heads, each with a crown radius of 2 meter, are used as end closure. Determine the thickness of the cylindrical shell and the torus spherical head. We will see the solution. Now given data. Operating pressure is equal to 0.75 megapascal. SYT, that is yield strength, is equal to 200 Newton per mm square. Corrosion allowance CA is equal to 3 mm. Internal diameter DI is equal to 2.5 meter. Crown radius L is equal to 2 meter. Step 1. Thickness of cylindrical shell. The design pressure PI is given by PI is equal to 1.05 into operating pressure. Therefore substituting the values, 1.05 into 0.75. Therefore PI is equal to 0.7875 megapascal. The weld joint efficiency for a spot radiographed double welded butt joint is 0.85. Therefore efficiency neta is equal to 0.85. The allowable tensile strength sigma T of the plate material is given by sigma T is equal to SYT divided by 1.5. 1.5 is the factor of safety. Therefore sigma T is equal to 200 divided by 1.5. Therefore sigma T we are getting it as 133.33 Newton per mm square. Therefore thickness of cylindrical shell is given by small t is equal to pi di divided by 2 sigma t neta minus pi plus Ca. Therefore substituting the values, 0.7875 into 2500 divided by 2 into 133.33 into 0.85 minus 0.7875 plus 3. Therefore small t, that is thickness of the cylindrical shell, we are getting it as 11.72 mm or which is nearly equal to 12 mm. Now we will calculate thickness of torus spherical head. Step 2. Therefore thickness of torus spherical head is given by T is equal to 0.885 pi into L divided by sigma T neta minus 0.1 pi plus Ca. Therefore substituting the values, 0.885 into 0.7875 into 2000 divided by 133.33 into 0.85 minus 0.1 into 0.7875 plus 3. Therefore we are getting thickness of torus spherical head as small t is equal to 15.3 or which is nearly equal to 16 mm. Therefore this is the end of the second problem. We will stop here. Thank you very much.